Do next is to discuss MOS models briefly. Again, this is not meant to be a detailed discussion on how to model a MOSFET. I think all of you know the square law model. That's what we are going to use. What I'll highlight is some important aspects of the model as well as look at the small signal model, both at low frequencies and particularly at higher frequencies. Okay, all the parasitic capacitors that come into picture. So, a MOS transistor has 4 terminals. The substrate, the drain and source, and the gate. Okay. And the substrate is also connected. So, it is usually connected by another P plus diffusion on the upper side. All the connections are from top, but for the purposes of discussion, I will show the connection here. Okay. So, the basic operation is very clear. Let us initially imagine that the two terminals are at the same voltage, that is, the drain and source terminals are at the same voltage. I will call this terminal the source and this is the drain, but as you know, the drain and source of a MOSFET are decided based on the bias. They are not some fixed terminals like in a bipolar transistor. Okay. So, as you go on increasing the gate voltage, there will be an inversion channel that will be formed under the gate, and that behaves like a conductance between the drain and source regions. Depending on whether drain is above or below the source, current will flow either from left to right or right to left. Typically, the lower potential is called the source. Okay. So, this is the symbol. If I have this, if I keep increasing the value of Vg, at some point the inversion will be formed, and that point is known as the threshold. And if Vd is greater than Vs, current will flow in this direction, and if Vd is less than Vs, it will flow in the opposite direction. So, it is an inherently symmetric device, but the way we model it is similar to the way bipolar transistors are modeled. So, we will end up with an asymmetric looking model. It is also symmetric. Okay. But first you have to identify which one the source is, and the source is the lower potential terminal. Now, in analog circuits, typically this is also fixed. You intend some particular terminal to be the source and you bias things that way in many circuits. There are circuits in which the source and drain can get interchanged. If you use it as a switch, for example, sometimes one side of the switch may be higher than the other, sometimes it may be lower. Okay. Now, another thing that can happen is during the operation of the circuit, because of some signal swings, the source and drain can get interchanged. So, you have to watch out for those conditions. So, sometimes you design something and you simulate it and it behaves in a slightly unexpected way. One possible thing, I mean, among many hundreds of possibilities, is that the source has become the drain and drain has become the source in some case. Okay. So, that you have to watch out for, because you typically identify one terminal as the source and you do your mental analysis, but then perhaps the voltages in the circuit are in the other way and then it is working in the opposite direction. Okay. What is the effect of the bulk terminal? What happens if I increase the voltage of the bulk terminal? Huh? Threshold will increase. Why? It will decrease. So, it will decrease, right? If I increase the voltage of the bulk terminal, the threshold voltage will decrease. Essentially, the amount of charge in the channel will increase. So, you can think of this as, think of the MOS, that is how it was initially conceived. There is this channel, okay, sort of semiconducting channel, and there is a capacitance to the gate and a capacitance to the bulk. So as you increase the voltage of the gate, more charge is placed on the plates, and similarly as you increase the voltage of the bulk, more charge is placed on the inversion layer. Okay. So more charge will be available for conduction whether you increase the potential of the gate or increase the potential of the bulk terminal. Okay. That's why it's called the back gate. In a way, it's exactly similar to the gate. The only difference is that the capacitance between the gate and channel is an oxide capacitance, and here it's a depletion capacitance. Otherwise, they do behave in the same way. You increase either the gate voltage or the bulk voltage, you can increase the amount of charge in the inversion region. Okay. So, in fact, some of the very recent circuits that were designed for in particularly low voltage supplies do use the bulk terminal. Normally, you tie it to the lowest potential in the circuit. Why is it tied to the lowest potential? So, the dangerous point is this: you don't want a forward bias junction between the drain and the substrate. Okay, and also typically, if you end up with one forward bias junction, if you have many junctions close together, you know about the possibility of CMOS latch up, right? So things can get forward biased and can get latched up in some particular state. So you can't have, although you can increase VB, you can't increase it too much. Okay. So let's say VB should be maintained less than the minimum of source and drain voltage, and possibly you can go about half a volt above it, but definitely not more. Then you will end up with a significant current through the forward bias diode. Okay. But there have been circuits made recently successfully in which you do forward biases by about 0.3 volts, thereby lowering the threshold voltage. Okay. A lower threshold voltage does have advantages in an analog circuit. And sometimes you can use both the gates to, like I said, the back gate and this gate are very similar. So you can also feed a signal to this and amplify it. Okay. So you can use it as an amplifier between the gate and drain or between the bulk and drain. That's also possible. So this is something like these are not the circuits that we will be discussing in this class, but these are possibilities that you should be open to, like when you read papers or when you design some circuits yourself. When you design something in a low voltage technology, perhaps you can access the bulk, bias it separately. Now, one of the constraints is that typically the substrate of the MOS transistors is common to all the MOS transistors on an IC. So you can't do this, because if you try to forward bias lightly forward bias one of the MOSFET junctions by 0.3, maybe something else has become strongly forward biased. But with PMOS you can do this safely. Okay. And also sometimes you have technologies in which both P and N are in separate wells. In that case, you can do the same thing for both of them. Essentially, a MOSFET is a voltage controlled resistor, and the controlling terminals are the gate and the back gate, and the terminals of the controlled resistor are the drain and source. Okay. Now, all of you are familiar with the square law of the MOSFET. Okay. So in this case, in keeping with the bipolar transistor tradition, you identify one of the terminals as the source. But this model works only if this is the lower potential terminal. Okay. If you do the opposite thing, it won't work. Right. So, and that is denoted by this arrow typically. And it refers to the current between the drain and source. That is current that flows from the drain to the source through the device. Okay. That is the model when VGS is greater than the threshold voltage VT and VDS is less than VGS minus VT. Okay. So, everything is referred to the source terminal. And sometimes this condition is easier to evaluate if you think of the potential between the gate and drain. Okay. Sometimes it is easier to think of it that way. So, you know how this happens, right? We have so this should be greater than VT, sorry. VGD is greater than VT. So, Cox is the capacitance density of this capacitance. Okay. And depending on the potential between the gate and a particular point in the channel, you have a certain inversion charge density. Okay. So, this condition says that there is inversion at this end, the source end of the channel, as well as on the drain end of the channel. That is, there is a continuous channel connecting the drain and source. That is when this equation holds. Okay. So, roughly speaking, you can think of here the charge density is related to VGS minus VT. Okay. And here it is at this point it is related to VGD minus VT. Okay. So, if you combine the two and sort of get an average charge and calculate the conductance of this part, you will get this equation. That is how that equation is obtained. Okay. Now, as we keep on increasing the potential of the drain, at this end of the channel, it is no longer inverted, the channel gets pinched off. After that, the drain potential does not have any influence on the current. That is the model of a basic MOSFET. Okay. Under some assumptions, that is true. So, in that case, ID becomes okay. So, after it gets pinched off, across the channel you will have a fixed voltage of VGS minus VT. That is the idea, and that is how we derive this model. Okay. This is for VGD less than VT or VDS greater than VGS minus VT. Okay. So, this is the saturation region of the MOSFET, and it is assumed that this is also strong inversion, right. That is why we get this square law. And this is the non-saturation of the triode region or the linear region, and this is also strongly inverted. And when VGS is less than VT, you assume that it is off. That is the very basic model of the MOSFET. Okay. Where is the bulk potential in this? VT is a function of, VT is typically expressed as a function of this bulk, and because the bulk is connected to the lowest point in the circuit, you do not measure it with respect to the source, you do the opposite. That is what is normally done. Okay. You refer everything with VSB instead of VBS. You can obviously do the other thing also, but it will always be negative in most circuits. So, how is VT related to VSB? So, there is a certain VT0, this is basically the threshold at 0 VSB equal to 0 plus there is some square root dependence on VSB. Okay. So, if you go on increasing VSB, you will have higher threshold voltages, and that can be a problem or a limitation in some circuits. Okay. So, there is nothing new here, it is just a very basic review of what you already know. Okay. So, from these equations also you can calculate the effect of the bulk potential, and you will see that as you increase the bulk voltage, you will end up increasing the current. Okay. Now, this is a very basic model that takes into account only the strong inversion region. It says that there is either strong inversion or no inversion, right. But in the middle there is a region where you get you have very weakly inverted channel, but you do have current conduction through it, and that is also an important region for circuit design. That is a weak inversion region. And what is the drain current in the weak inversion region? So, it behaves like a diffusion device, and it has an exponential dependence on VGS, and this V lowercase t is the thermal voltage, and there is something that can be expressed roughly like the saturation current. Okay. And the saturation current will be proportional to the width of the MOSFET. So, everything, all currents are proportional to the width of the MOSFET always, because if you take two transistors in parallel, two identical ones, put them together, you get twice the current. That is simply like increasing the width by a factor of 2. So, the proportionality to width is pretty much exact for MOSFETs in all regions of operation. Okay. Now, this is a factor which is maybe 2 to 3 in a MOSFET. Okay. In a good bipolar transistor, it is 1. In a MOSFET, it is about 2 to 3. Okay. Now, this also holds. Again, this does not. The equation I have written does not show any dependence on VDS. Okay. So, this holds only when VDS is above a certain limit, which is about 3 times the threshold voltage or so. Okay. Sorry, 3 times the thermal voltage. Now, we will see why later. This is also an important region for operation, especially for low power circuits. Okay, the bottom line is you get a larger transconductance for a given bias current in the subthreshold region. Okay. As you reduce the current density in the MOSFET, you keep getting larger and larger transconductance for the same bias current. So, that's an important motivation for using it in lower current densities or going towards subthreshold region. Okay. I am assuming that all of this does not need any further explanation, right? I think you know the basic model. Everyone is familiar with this, right? All of this. Okay. So, if you look at these models and plot the familiar ID versus VDS curve, and here again I am going to plot it in strong inversion. The current will go as some inverted parabola for some time, and then after that it stays constant. That is what the model says. And if you increase the value of VGS, you will get a higher saturation current, and if you increase it by an equal amount of VGS, you get even larger step. Okay. This is because the current is dependent on the square of the gate source voltage. Okay. So, this is the ideal characteristics of the MOSFET, but we also know that it does not stay absolutely constant. What happens to the current here in this region? Why? So, what happens? Current here. So, it gets pinched off here, and as you increase the drain voltage, the depletion width increases in this region. It pushes the pinch off point closer to the source. So, effectively, it's like the length of the channel has reduced. Okay, the same voltage drops across a smaller length, so that means a higher field and a greater current. Okay, so the same equation holds if you make L dependent on VDS. Okay. So the current in this region would be this is the L prime, which is a function of VDS times VGS minus VT square. Now the dependence of L on VDS is some complicated thing which we are not particularly interested in. We want a more usable model for design, in which case we simply write this as okay, and this L prime is nothing but L minus something, okay, some effect of VDS. So this entire fraction can be written as 1 plus, okay, and this is further simplified to a first order dependence on VDS. Okay. So this lambda, I mean, if you expand this in a Taylor series, you get something, and the first term is what we get, what we account for in the model. And also you can see that this delta L is a function only of the drain voltage. Okay. So this lambda itself will have a 1 over L type of dependence, okay, because regardless of how long the channel is towards this side, the amount of distance by which the pinch off point moves is dependent only on this voltage. Okay. So as a fraction of the total length, the movement of the channel reduces. So that means that if you start off with a very long channel, the amount of changes, the relative change is very small. Okay. So that's why the lambda is dependent on L, and it's inversely proportional to L. So this means that if you don't want this effect, you have to use longer channel lengths. Okay. So a more complete model is lambda is inversely proportional to L. Of course, we now know that even this model is quite incomplete. There are all kinds of other constants that come into picture, and the actual model that you use for simulation, the BCM3 model, has about 150 constants in it. So we do some analysis with this basic model and go with it, get some intuition from it. But then for exact analysis, you have to go and resort to the simulation. Okay. Now in modern MOSFETs, if you plot ID versus VDS for different values of VGS, you will get something like this. Okay, let's forget the fact that the slope I have shown is 0. For equal increments in VGS, you don't get a very large increase in the increments in current. Why is that? Why? Yeah, what is the effect? So what I am saying is, before, let us say you had delta, so VGS1 plus delta V, VGS1 plus 2 delta V, and so on. So if you did this, if you plotted it for equal increments, it would go as square law, okay, or if I plotted versus VGS in saturation region, it will do something like this, but now it will probably do something like this. Why is that? Velocity saturation, yeah. So what is that effect? Yeah. So because of velocity saturation, even this square law dependence does not hold, okay. So you will get something like, so originally the model was okay, ignoring the channel length modulation. Now what was this? This was really the charge density, which is related to Cox and W, and mu times VGS minus VT by L. What is this? What is this quantity? Huh? What? Drift velocity, yeah. VGS minus VT by L. We said the voltage across the pinched off channel is VGS minus VT. The field is VGS minus VT by L. And the velocity is mu times the field. So it is mu times VGS minus VT by L. Okay. Now, after a point, the velocity is not dependent on the field anymore. The velocity saturates. So this entire thing is replaced by where this is the saturated velocity of the carriers. Okay. So this is the model under velocity saturation, where the dependence on VGS minus VT is not square, but a direct proportion. Is this okay? So what happens in a regular MOSFET is, as you keep on increasing the VGS in saturation region, the charge density increases and also the voltage across the pinched off channel increases. So the field increases and velocity increases. So both the charge density is larger and they are moving faster. So you get more current. Now in velocity saturated regime, only the charge density is increasing, but the velocity is not increasing. That is fixed. So you get a direct proportion. You get only one VGS minus VT term. That is because of increase in charge density, not because of increase in velocity. I mean, reality, it's not like there is some abrupt transition between velocity saturation and linear region. So if you plot the velocity of the carrier versus the electric field, it does also show some linear dependence initially, but after a while it will do something like this. Okay. So the MOSFET, as you reduce the length of the channel, depending on, this also depends on the bias, right? This depends on how much field you try to apply. If you are operating here, then there is no velocity saturation, and if you are operating here, it is neither constant nor directly proportional to the electric field. So there will be some smooth transition between the two. It goes from being roughly like square law for long channel lengths to somewhat being proportional for shorter channel lengths. Okay, there are a lot of other complicated short channel effects as well, but this is one important thing. So you can try and play with your simulator. If you plot this ID versus VDS for the minimum length transistor, you will get, you will not get a square law type of increment in drain current, but if you do it for, let's say, 10 times the or 20 times the minimum length, you will probably get a more squarish law. Okay. We will see the implication of this. So clearly, I mean, you can see it directly from the picture here. If one of the curves is like this and the other one is like this is ID versus VGS. So one of them has a smaller transconductance than the other one. Okay. Is this okay? Now, the model for the PMOS transistor is the same, except that all voltages and currents are reversed, right? this is an NMOS. So if this is the source, it operates with a positive VDS, positive VGS, okay, and a positive VSB. A PMOS transistor will have a positive VSG, positive VSB, and the current will be like this, right? This is going from drain to source. Here it is going from source to drain. Okay. And it will also have a positive VBS. So this is the correct notation, but what we'll do is we'll flip everything. I mean, it's mentally clear what the polarity of the voltages should be for the transistor to be on. And I don't want to have to like flip between VGS and VSG or put minus VGS everywhere and so on. So we'll continue to call this, although this is VSG, we'll call this VGS. When I say positive VGS, it's understood that it is whatever the voltage is required, whatever voltage is required to keep the PMOS transistor on. Similarly, when I say VDS of a PMOS transistor is some 300 millivolts, I don't mean that this is more than this by 300 millivolts. I mean that it is in the saturation region and the polarity is whatever is required. Okay. That will simplify the notation. This is obviously confusing, but once you are familiar with the operation of the MOS transistor, this is better. Okay. So we can discuss PMOS and NMOS in the same way without worrying about too much about the rigor of the notation. Okay. Now, if you are very uncomfortable with it, you can at least put for the MOSFET, for the NMOS, we have mu Cox W by L, VGS minus VT square. For the PMOS, the current direction is opposite and VGS and VT are both negative. So you can imagine something like this and assign the right direction for the current. Okay. So I won't talk about VSG, etc. It will be always VDS, VGS and VSB. Okay. What's that? Oh yeah. Thanks. Now the other difference between, what is the other difference between NMOS and PMOS transistor? What's the main difference? Mobility is mobilities are different. PMOS mobility, that is mobility of holes, is about 1/3 that of electrons. So for a given geometry and given bias, assuming both have same threshold voltage, you will have lesser current in a PMOS transistor. So that also has some implications on circuit design that we'll see afterwards. Okay. Any questions so far? So again, this is nothing but things that you know, but just to clear out the notations and maybe a very mild refresher. Okay. No. Oh yeah, we'll come to that when I discuss the models. I'll show you. Okay. The GM of the transistor is higher, meaning for the, if you have two devices, one of which is operating in subthreshold and carrying, let's say, 1 microamp, other one is operating in strong inversion, also carrying 1 microamp. The GM of the subthreshold transistor will be higher. But for this to happen, you know that the subthreshold transistor has to be a lot wider, right? So it's carrying the same current, it's much wider. So that's why the GM is higher. So if there are no questions on this, we'll stop here and move on to the small signal model. Okay. The drain current is a function of VGS, VDS and VBS. It's some nonlinear function. Okay. Now, what does the small signal model represent? It represents increments in these quantities, right. So, let us say it is operating at a particular value of VGS, VDS and VBS, which gives you a particular value of ID. Now, let us say I apply increments in the applied bias voltages. I get a different current, which can be thought of as an increment over the first current. Okay. Now, this also can be derived using the same nonlinear equation that you are familiar with, or I mean, in some cases it's complicated, but once you know this function f, you can calculate the current for any combination of input variables. But you do want to simplify your life by calculating only the increment. You don't want to go through this nonlinear calculation anymore. So, first of all, we know that in all of these nonlinear functions can be represented as some Taylor series expansions. So, and for a small enough increment, you can always find a small enough increment for which only the first order term of the Taylor series is significant. Okay. I will expand the function about this operating point, and this will have at a particular value of VGS times VGS plus at the bias point plus it will have lots of other terms, which includes higher order terms in each of these variables as well as cross terms. That is, you can have terms that have products of increment in VGS and increment in VBS and so on. Okay. So, we neglect everything else, okay, and retain only the first order terms. So, the virtue of the first order terms is that they are related to the increments in the voltages by a linear relation. Okay. Basically, they are a linear combination of the increments in the cause. So, the cause of the current is VGS, VDS and VBS, and the current is some complicated nonlinear function of this. But if you increment each of these quantities by a small amount, the resulting increment, if you notice, this part is nothing but the original current, the bias point ID. So, this cancels with this. I can relate the increment in ID to increments in the voltages, the terminal voltages, as a linear combination. Okay. And the coefficients of the linear combination are the derivatives of the nonlinearity at a particular bias point. Okay. So, you have a certain set of voltages applied to the MOSFET, you get a certain current. Let us imagine a small change in the applied voltages, you get a different current, which can of course be calculated from the nonlinear function. If you know the nonlinear function, you can calculate it. But let us say what happens when we expand the nonlinearity as a power series. Okay. So, about the operating point that we chose. Okay. This is the operating point is something that we choose. We can think of anything as the operating point. So, in this case, the particular values of VGS, VDS and VBS are the operating points. So, it will be the function at that plus the first order terms, that is the derivatives with respect to the terminals times the increments plus higher order terms and so on. And for a small enough increment, I can possibly neglect all of the higher order terms. I can certainly find a small enough increment where that happens. Okay. So, after that I will use only this part, and you recognize this as being the original bias current. Okay. So, here I am left with only the increment, which is related to the increments in the input voltages as a linear combination. Okay. That is the virtue of the small signal model. For a small enough increment about a bias point, you can relate the increment in the current to increment in each of the voltages independently. Okay. In reality, it's a nonlinear function. If I look at this entire series, I'll have terms like VGS times VDS and maybe even more complicated products. Okay. But for a small enough increment, I can ignore all of that. I can think of VGS causing a certain increment in ID, VDS causing a certain increment in ID, and how much increment it causes, basically these coefficients depend on the bias point and the nonlinearity. Okay. Is this okay? So the virtue of the small signal model is that it is linear. So there are many advantages to that. First of all, there is a large body of analysis related to linear networks that we can use when we analyze something like this. Okay. When I say linear, I mean that ID versus VGS is linear in the small signal increment sense. Similarly, ID versus VDS is linear, ID versus VBS is linear. By definition, you expand the nonlinearity and throw out everything other than the first order term. So by definition, the small signal model is linear. Okay. So it is much more convenient for analysis, for calculating increments and so on, because it's these nonlinearities are very complicated, hard to predict, but the small signal models are easier. Okay. And the other thing is, many times you do want the circuit to behave in a linear fashion. In fact, in those cases, effectively what you are doing is trying to make this part much more dominant compared to any other nonlinear term. In those cases also, because you deliberately try to make the circuit as linear as possible, the small signal analysis is even more valid. Small signal analysis keeps only the linear terms and throws out everything else. So if you end up with a linear circuit, then clearly it is valid. Okay. Is this clear? So this is kind of arbitrary in that I have some values of VGS, VDS, VBS and some other value and some other value and so on. For each of these, I could calculate the current independently. But my life will be easier if I think of one of them as the bias point and expand the series around it. I have to do it only once. Then I calculate the coefficients and that's it. After that, for every other value of VGS, VDS, VBS, I only look at the change from my chosen bias point. Okay. And I have the coefficients, so I can calculate ID, the increment in ID as a linear relation to those increments. Okay. Now the problem is, of course, maybe the bias point I chose and the point I want to calculate are far from each other. That is, the increments are not really small. In that case, the small signal analysis will give you errors. Okay. So I have to be aware of that fact, but beyond that it will work. Okay. So it is convenient, it is linear, but it holds only for small signals. That's the bottom line. So what is and you can do this for any device, right? This has nothing to do with a particular nature of a MOSFET. Any device in which some quantity is nonlinearly related to all other quantities, let's say the cause and effect are nonlinearly related, you expand it in a series and you throw out everything other than the first order term and you come up with the small signal model. Okay. And you, I think, are already familiar with the small signal models of a diode and a bipolar transistor and MOS transistor and so on. So if I look at only the increments, this is what I have. At a particular value of VGS, I'll call it, instead of this, I'll say at the operating point. Okay. Times the increment in VGS plus the derivative with respect to VDS at the operating point times VDS at the operating point times VBS. Okay. So typically a transistor is drawn like this with the source at the bottom. Okay. And what is this ID? It is the incremental current, increment in the current flowing from drain to source. And these are increments in voltages applied with respect to the source. Okay. So again, this is not the applied voltage between drain and source, but this is the increment in the applied voltage between drain and source. Okay. So what is the small signal model? What are the circuit elements in the small signal model? Here it is the causes are voltages and the result is a current. So, it is a voltage controlled current source in general. Okay. So, similarly, if you had some controlling current, it would be a current controlled current source and so on. So, for each of these we have a current source. And this constant, which relates the increment in ID to increment in VGS, is known as the transconductance GM, okay, because it has dimensions of conductance, but it is the increment that is transferred from one set of terminals to a different set of terminals. Similarly, this derivative with respect to VBS is known as a transconductance from the bulk source terminal, okay. So, this is the drain, this is the source, we have GM times the increment in VGS, okay. Sorry, this I said is the source, and VGS is applied between the increment applied to the gate and source. Similarly, I have another control source here, which is GMBS times VBS, and the controlling quantity is this EBS. I think we need to do something about the screen. Okay. Now, the third quantity here is the increment in current between drain and source as related to the increment in voltage between drain and source. So, the voltage increment and current increment are between the same terminals. So, it is a transconductance connected back on itself. It is basically just a conductance, okay. And this is known as the drain to source conductance GDS, okay. I can represent it as a control source, but I know that the controlling terminal and the control source are across the same 2 points. So, I represent it as a conductance, okay. So, this is the basic small signal model of a MOSFET, okay. We already know that the gate current is 0 and the bulk current is 0 in the regions that we want to operate. The bulk current can be large, but we do not want to go into that region. So, we will not consider that anymore, okay. As far as the DC picture is concerned, the gate current is 0, so the incremental gate current is also 0. Similarly, the bulk current is always 0, so the incremental bulk current is 0, okay. And this is a model that we will use very frequently in circuit analysis, okay. And the increment between these two is VDS, okay. So, this is a DC or the low frequency small signal model, because we have not considered any capacitances or charge storage effects so far. Any questions on this? Okay, so next class onwards we will go on to the AC small signal model and then see some of the what each of these comes out to be. Okay, we already know the nonlinear function f, so we can calculate each of these by differentiating the function. Okay.